All right, so we're going to have our second quiz after class today. So I will finish the lesson around 7:30, 35-ish. So you can start your quiz. It will pop up on your course material screen around 7:36 p.m. I think that's the time I set up for. And then once you start, you have 20 minutes to finish. And before 8:10, everyone should be done with the quiz. Okay? So, any questions? So, usual 20 minutes quiz. Okay? And there's going to be 3 questions. This time I made it shorter. But again, you have to time yourself well enough so you don't run out of time. Okay? Don't spend more than 5 minutes in a question. If you're spending more than 5 minutes, then you have to learn how to time yourself. Okay? So learn how to speed up. So once you start the quiz, you will see. For now, I'm gonna start our lesson for today. I don't want to give out too many details about the quiz. Greg, do you have a question?
Yes. As far as the quizzes go, are we allowed to go back now, or is it still if we submit an answer, that's it?
Yeah, same thing. You can go back.
Okay.
Yeah, it's part
we can.
security. You can't.
Oh, cannot. Okay,
Yeah,
got it.
right. It's for security reasons. Okay.
Oh, okay.
Yeah, so just make sure you carefully read the question, answer the question, carefully pick your choice for that question. Okay?
Got it.
All right. Okay. All right. So I'm going to go ahead and start. And again, let me know if you guys have any questions. You're welcome to speak through your audio. So let's start our lesson for today. So today we're going to be so before I start, I'm going to give you a brief summary of 2.9, what we covered last time, and then we'll start with chapter 3. So, okay.
Professor?
Driz, yeah, do you have a question?
Didn't we end on a question last time?
We ended with the question from 3.1, but we didn't solve it, right?
Yeah.
Yeah, so I'm gonna pick up from there.
Okay.
All right, so today is June 16th, 2020, and this is our lecture 7. All right, so far from 2.9, so let's just recall from 2.9, we discovered 3 different ways we can do second order, but very particular second order equations. So we talked about reduction of order, and there were 2 different scenarios you can use reduction of order. One, when our independent variable is missing. So that means either t, which we consider to be our independent variable, or x, these variables are missing from the given equation. So if that's the scenario, then you would treat it as solving it using the following substitution. So you use the substitution v equals y prime. So that means v prime is going to be y double prime. And then we started kind of rewrite v prime as v dv dy equals y double prime. So we kind of rewrote v prime using chain rule. So this is the substitution you want to use when you have independent variable missing from the equation. And the procedure, you can look it up on our previous notes from last time. And the second scenario we had was, what if the dependent variable was missing? So when our dependent variable is missing. So our dependent variable is always y for this case. So if that's the scenario, then we're going to use the substitution. Again, v is equal to y prime, and then v prime is going to be y double prime. And for this one, you don't have to rewrite using t or y because you have the independent variable in the picture, so that's fine. So this is the substitution you'll plug in to your differential equation and just follow the procedure. And then we talked about what if we have a Bernoulli equation. So we worked on a method to solve Bernoulli equations. So Bernoulli equations are equations in the form of y prime plus p of t times y is equal to q of t times y to the nth power. So nth power. Now if n is equal to 0, then it is separable. So you would use separation of variable to solve it. If n is 1, it is linear. So you would use integrating factor to find solution. But if n is anything other than 0 and 1, then you would use the following substitution. Well, we use if n is greater than or equal to 2. But n could be anything. N could be a negative value as well. But we don't really talk about those cases. So let's stick to n is greater than or equal to 2. So you would use the substitution v equals y to the power 1 minus n. And then from here, you know how to proceed. Somehow, when you make the following substitution and compute y prime, you will have a linear equation. So a nonlinear becomes a linear. So that's the idea with this substitution. So that's what we talked about last time. And then we moved on to chapter 3. So that was the end of chapter 2. Okay? Any questions on that? Okay, so then we started talking about chapter 3, where I start introducing second order homogeneous differential equations. So chapter 3, the entire chapter 3 we're going to study second order, and we'll learn different methods how to solve them. So we started with 3.1, which is second order homogeneous with constant coefficients. So second order homogeneous with constant coefficients. Okay. So the form that we're looking at is of the following. We have y double prime plus p of t times y prime plus, I believe I wrote q of t, but again, they are just constant, times y equals to a function g of t. Now, this is in standard form. Now, if g of t is 0, then this is a homogeneous second order. Okay. So then we have the following form. We have y double prime plus p of t y prime plus q of t y equals to 0. So that's the case we're going to focus on right now, on 3.1. How do we find solution to this differential equation? So let me run you through with the example we started last time. So let's consider the following example. So say we want to find general solution of the differential equation y double prime minus 4y prime plus 3y equals to 0. So this is second order. It's homogeneous because the right side is equal to 0, and the coefficients are all constant. So this is a constant coefficient homogeneous second order. Now, what is the solution to this? Well, we're going to come up with a guess, an ansatz. That's what we call it. It's an educated guess. So we're going to assume that the solution has the following from. Assume that the solution y is equal to e to the rt. So this is what we call an ansatz. This word ansatz, it just means a guess. Okay? So this is sort of like you're guessing what the solution could be for this particular differential equation. So if we're assuming this is the solution, well, that means we have to compute its first derivative, second derivative, plug it in, and see what is r equal to, right? That's the idea. Okay, so let's go ahead and do that. So I'm going to compute its y prime. So r is a constant, t is the variable, so this would be r e to the rt. That's the first derivative. Let's compute the second derivative. So that would be r squared e to the rt. Okay, so I have an expression for the first derivative, second derivative, and y. So I'm going to go ahead and plug them in. So this is y prime, y double prime. And we're going to substitute these into our differential equation right here. And then we'll try to see if we can solve for r. So we have r squared e to the rt minus 4y prime. Well, y prime is r e to the rt plus 3y, y is e to the rt, equals to 0. Okay? And now we do some algebra. It looks like they all have e to the rt in common, so let's factor e to the rt. So then we're left with r squared minus 4r plus 3 equals to 0. So that's the next step. Well, now here is something you want to remember. This is a very important step. This piece right here, we have a name for this. So this is what we call the characteristic polynomial. Okay, now if you look at your differential equation that was given to us originally, it was y double prime minus 4y prime plus 3y. And now if you look at the characteristic polynomial, we have r squared minus 4r plus 3. So you should see that connection that y double prime kind of looks like r squared, right? Double prime, r squared. And then y prime looks like r to the 1 power. And then y, well, r to the 0th power, that means it's just 1. So it's just a constant. So when you see you have a second order, you can always jump right to the characteristic polynomial. You don't have to go through all those steps, okay? So that's why this is very important. So now we want this equation to equal 0. Well, the exponential part can never be 0. So e to the rt, this will never be 0. So we can't really solve for r. But r squared minus 4r plus 3 equals to 0. Now this you can solve for r. How do we solve for r from this equation or from this polynomial?
Use the quadratic equation.
Right. So here you can use.
Or you can just use the factor.
Exactly. So you can do quadratic formula, right? It's a quadratic equation. So you can have quadratic formula. You can do factoring. Do you guys remember the quadratic formula? Yeah, right? It should be like on top of your head. Never forget. Never forget the quadratic formula. It's always your best friend. And factoring is always nice. So if you can factor, I would say use factoring first. If factoring fails, then we're looking at a different route. So quadratic will work all the time if it's a second degree. So for this one, I would go with factoring because it looks like this is factorable. So I can factor this into r minus 3 and r minus 1. Okay, so that was success. Now we can set each factor equal to 0. That's one of the law from algebra. So we have r minus 3 equals to 0. And we have r minus 1 equals to 0. Hence we have r is equal to 3. So that's nice and neat. And r is equal to 1. So there you go. We have two values for r. So now what is our solution? Well, we assume that the solution is in this form. Assume y is equal to e to the rt. So that means all I have to do is plug in the value for r. So our solution is going to be y. So let's say first solution, y1 is e to the rt. So r is 3t. And our second solution, y2, is e to the 1t. So it's just t. Now, what you want to do is you want to, so this is a theorem from 3.2 that I'm going to explain later on, but we're just going to use it right now because it just makes our solution looks more accurate and it gives us the general solution. So what are we going to do? We're going to put the two solutions together and write their linear combination, and that will be the general solution. So I'll explain what all of this means in 3.2. So our general solution is going to be y equals c1 e to the 3t plus c2 e to the t. So that's the general solution. So when I said the word linear combination, do you guys know what that means? Have you guys heard that before? So this is the linear combination. So linear combination of y1 and y2. So the word linear combination, it means you take the two solutions, they're independent, and you multiply them by a constant. So I'm using c1 and c2, and you add them up. So you multiply them by constant and you add them up together. That's the linear combination of y1 and y2. That's just another terminology you added to your dictionary, and we'll be using it very frequently for chapter 3 and on. Okay. Now you see it's a second order, so you get two independent solutions. Any questions for this method? So that's the method of solving second order homogeneous constant coefficients. They're kind of fun, right? Yeah. So let's now, how would you find C1 and C2? So before I move on to another problem. What do you guys think? So if you think about first order, if I give you, we only had one constant, C1, right? So Carolyn, you're absolutely right, initial value, and Greg as well. First order, I give you one initial condition, so you found C1, one constant. Now for second order, well, we have two constants, so we need two initial conditions, okay? So if I impose two initial conditions, we can then solve for C1 and C2. Okay, so we'll do that later on. Now let's do another problem. just finding the general solution. Now we don't have to go through all of these steps that I did with ansatz. You can straight jump to the characteristic equation. Okay, so that's what we're going to do the next equation. So here's our example 2. So let's compute the general solution. So say you have y double prime plus 5y prime plus 6y equals to 0. So I will give you a few seconds for someone to tell me what will be the characteristic polynomial. So just take a few seconds. So remember, we're assuming, so you should remember that the solution looks like y equals e to the rt. That's what we're assuming. So Shuman says r squared plus 5r plus 6. Absolutely right. So we have r squared plus 5r plus 6 equals to 0. So right away you can jump to the characteristic polynomial. You don't have to show all the derivatives part, because the exponential term, if you go back, is not going to give us a value for r. So we can ignore that step. So any questions on that? Now the rest is algebra. You have to kind of know how do you solve the second degree polynomial. So we have techniques, quadratic formula, or factoring. So I'm going to go ahead and see if I can factor this. So is this factorable? Yeah, right? Yeah. So we have r, right. So Wasi, yes, we always assume that the solution is the exponential e to the rt. And then the goal is to find r. So r plus, so 3 and 2 would do, right? So Sadia, you're right. R is negative 3 and negative 2. So I have r plus 3 and r plus 2 equals 0. So therefore, we know r is equal to, so you can say r1 is equal to negative 3 and r2 is equal to negative 2. We have two different roots, okay? So that's important. I didn't mention that over here, but I should. Let's say r1, r2. Okay? So what is our general solution? So our general solution, it's going to be the linear combination of y1 and y2. Now again, you can write those out, but I'll give you the general solution. So that would be c1 e to the r1t, that's negative 3t, plus c2 e to the negative 2t. So that would be our general solution. So any questions on this? Okay. Now let's stop for a moment and think about this. Now, if you're looking at a quadratic equation, do quadratic always have real roots? Let's think about it for a second. No, right? Right, so the answer is no. Quadratic, they can have two real roots. For example, this case, we have two distinct real roots. Quadratic, they can also have imaginary roots, right? When you can factor, you start using the quadratic formula and somehow you get a negative value inside the radicand, and that makes into an imaginary root. Now you can also have repeated roots, right? So those are the two different scenarios we're going to talk about later in chapter 3. So 3.3 and 3.4, I believe. We're going to talk about how to write solution for complex roots and how to write solution if the roots are repeated. Here we have real distinct roots. So we're on the case real distinct roots, where the solution is the exponential. When it's not real and not distinct, you have complex and repeated, then the solution will vary. So I will do that as we go along, okay? So for now, let's just focus on real, distinct root. Alright, so let's do another problem. So that's just something to keep in mind for the future, that we could run into roots that are not just real and distinct. So here's our example 3. Now for this one, I'm going to do an initial value problem. So let me know if you guys have any questions so far. So let's solve the initial value problem. So suppose we have y double prime minus y equals to 0 with the initial condition y of 0 is 2 and y prime of 0 is negative 1. So we impose a condition on y and we impose a condition on y prime. So I will give you a few seconds just to come up with a general solution. Alright, so let's jump to our characteristic polynomial. So again, you should be thinking that the solution has the form y equals e to the rt. That's how the solution would look like. Okay, so we'll have that on the side. So what is the characteristic polynomial for this second order equation? Almost, Sadia and Suman.
Isn't it r squared minus 1 equals
Right.
0?
Exactly. So let's show work. Why isn't it r squared minus r? Right, so you guys see it? Right, so if you were to go through the long way, so yeah, so let's just show more work and then we'll get to characteristic. So if y is equal to e to the rt, that's what we're assuming. That means y prime is r e to the rt, y double prime is r squared e to the rt. Now let's plug this in. So we have r squared e to the rt minus e to the rt equals to 0. Again, we factor out e to the rt. So, yeah. So you'll have r squared minus 1 equals to 0. So that's the characteristic polynomial we're looking at, r squared minus 1. So be very careful. Sometimes you might feel like y replaces an r, but it doesn't. Only derivatives will replace with an r. So if you show more work, you would see that. So now if we take it from here, we have our characteristic polynomial to be r squared minus 1 equals to 0. So we have r1 is 1, r2 is negative 1. So we have two distinct real roots, so we know the solution looks like. So our solution would be y equals c1 e to the rt, but we know what r is. Our r's are 1 and negative 1 plus c2 e to the negative t. So that's the general solution. But we want the particular solution that satisfies the initial condition. So we're going to go ahead and impose those. So the first one we have is y of 0 is equal to 2. So if we plug that in, we have, so t is equal to 0, y is 2, 2 is equal to c1 plus c2. Now the second initial condition is imposed on the derivative of y. So we're going to go ahead and compute the derivative of y. So we have y prime. So y prime will be what? C1 e to the t minus C2 e to the negative t. And now we can impose the second condition, which is y prime of 0 equals -1. So that will give us -1 is equal to C1 minus C2. So we're solving two equations. We're solving this one and we're solving this one. So you have a system of equation now. So think of as C1 and C2 are your variables. How do we solve this? Do you guys remember this? So let's do some algebra. So we have two equations. 2 is equal to C1 plus C2. Then we have -1 is equal to C1 minus C2. How do you solve for C1 and C2 from here?
Fill out the C2, and then you add 2 and -1.
Yep.
So you have 2, so you have -2 is equal to 2C1. No, sorry, you have 1 is equal to 2C1.
Yeah. All right. So I'm going to go ahead and add them. We're going to add them because you see that when you add these two equations, C2 will drop because they're differ by a sign. So we have 1 is equal to 2C1, which means C1 is equal to 1/2. Oh, that's nice. Okay. Well, now that we know what C1 is, so Anik, you already have the answer for C2. You can plug it in, right, into any of these. So I will go ahead and plug it into that. You will have C2 is equal to, so it looks like it's going to be 3/2. So Anik, thank you. So there you go. You have the solution to the initial value problem. So our particular solution is going to be y equals C1, which is 1/2 e to the t plus 3/2 e to the negative t. So that would be our solution to this problem. Any questions, guys? Oh, so it looks like I couldn't make a box. Almost, yeah. Okay, so any questions on this? How do you guys feel? Okay, so Bethany feels good. That's good. Now let's do an example. Slightly different. So this is a problem from the textbook. It's an actual assigned problem. So let me just pull up that page on my book. So what would be the characteristic polynomial for this? So we have, so Sadia, you're almost right. So it should be 4, right? So 4r squared, right? Because it's y double prime. Good catch. Right, so Sadia, I think you just mistyped it. So we got it right. So we have, so our characteristic polynomial, it's going to be 4r squared minus 1 equals to 0. And then we try to factor this. Now, because this is the section where finding real distinct root, we can kind of go ahead and factor this. Or you can just solve it, right? So I'm going to go ahead and subtract 1. We have 4r squared is equal to 1. So r squared is 1/4. So that means r is equal to plus and minus 1/2. right? So those are the roots for r. Can you guys hear me?
Yes.
Okay. All right, so hopefully my device is working. So now let's write out the solution to this. No, I forgot to give you initial conditions for this. So the initial conditions are y of -2 is 1 and y prime of -2 is -1. So those are the initial conditions, which I forgot to mention in the beginning. Okay, now let's go ahead and write out the general solution. So we have our solution is equal to C1. So we have y is equal to C1 e to the 1/2 t plus C2 e to the minus 1/2 t. So that's the general solution. Now let's apply our initial conditions. Y of -2 is 1, so we have 1 is equal to C1. So okay, so it doesn't look like it's so nice, right? So if I plug in -2 for t, we have e to the -1 for the first term, and then for the second one we have c2 e to the what? +1? Yeah. Okay. Now let's find the derivative of y. So y prime is equal to 1/2 c1 e to the 1/2 t, and then minus 1/2 c2 e to the minus 1/2 t. So those are the derivatives. Now let's impose the, so y2 is so y of -2 is 1, not -1. Y prime of -2 is -1. Okay, so those are the initial conditions. Okay, yeah, it's okay. So now let's impose the initial condition on the derivative. So y prime of -2 is -1, so that gives us -1 is equal to, so plugging in -2 for t, we have 1/2 c1 and e to the -1, and then minus 1/2 c2 e to the +1 now. Okay, so here you have a system of equations. So now how do you solve this? How do we find values for C1 and C2? What do you guys think?
You have to multiply the top equation by 1/2 to cancel out the C2 and the E. I mean the 1/2 C2 and E.
The top one or the bottom one? I think, so I'm gonna go with multiplying the bottom one by 2. Okay, so that way I can get rid of the fractions. So we have the top one remain unchanged. So we have 1 is equal to C1 e to the -1 plus C2e. But the bottom one, we can get rid of these fractions. So we have -2 is equal to now C1 e to the -1, right? There's no more t. And minus what? C2e. So this looks a bit more simpler than what we had initially, right? Any questions? So now, what can we do now? What do you guys think?
C1 is equal to negative E.
C1 is equal to negative. Probably, but let's, so from here what I'm gonna do, I can add them up, right? Because if I add them, C2 will cancel out. So that would give us, so what will that give us? We have negative 1 is equal to C1, 2 C1 e to the negative 1. So we're able to solve for C1 like this. So that means, so let me bring it on this side. We have C1 is equal to, yep, so Sadia, you're almost right, but you forgot the negative. So it should be negative E over 2, right? So that's C1. So we have successfully solved for C1. Okay, right? And now, how do you find C2? Well, that should be simpler, right? You just plug it in to any of these. So I'm going to go ahead and plug it into the top equation because it looks simpler. No other reasons. So we have 1 is equal to C1. Well, C1 we just computed, that's negative E over 2 times 1 over E. So I'm just rewriting E to the negative 1 as 1 over E plus C2 E. So that gives us 1 is equal to negative 1/2 plus C2E. So what is C2 then? So I'm going to go ahead and add 1/2 to both sides. So that's 3 over 2 is C2 times E. So that means, so Anik, I think you forgot 3/2. So it's not 1/2, it should be 3/2, right? So C2 would be 3 over 2E. That's going to be C2. Okay? So any questions on this? That's pretty cool, right? They're not nice, but we can still work with them, so why not? So we have C1 and C2. Now if I plug these into my general solution, which we computed right here, that will give us the general solution to this. So we have y equals C1, which is negative E over 2 E to the 1/2 power, and plus C2. What is C2? That's 3/2 E to the negative 1/2 T, right? Yep. So that's, I think I forgot the E for this one. So that will be our particular solution for this. Now you see both terms are exponential. So now, what happens, so any questions on this? Any questions on computing the solution and then applying initial conditions to find the values for C1 and C2? Any questions up to here? So can we simplify this more? Yeah, we could simplify them. So if you were to keep going, we can kind of combine the bases, right? So we have negative 1/2 E and then E to the 1/2 T. And the second one, we have 3 over 2 e to the minus 1 times e to the negative 1/2 t. So by rewriting this in this particular form, we can also rewrite y is equal to negative 1/2. So for the first term, we can just add up their exponents. So it's 1 plus 1/2 t plus 3/2. And then the second one, we can also add up the exponents, negative 1 plus 1/2 t. So that's the furthest we can go to simplify this, right? So any questions up to this point? Okay. All right. So now, what can we say about this? What can we say about this solution? We want to describe the behavior as t goes to infinity. So let's take the limit, right? So I'm going to go ahead and take the limit as t approaches infinity of y. So we have the following limits to compute. So y is negative 1/2 e to the, so I'm going to rewrite the exponent in this form so it looks nicer. So I'm going to write it as 2, so that's 2 plus t over 2. Okay. And then for the second part, I can also write it as the same base for the exponents. So we have 3/2 e to the minus 2 plus t over 2. So I just rewrote the exponents. Hopefully this will help us to take the limit. Okay? Alright, so now as t goes to infinity, what happens to the solution? How does it behave? So what happens to the, so let's focus on one piece at a time. What happens to this expression right here as t goes to infinity? What do you guys think? Right, so Carolyn, you're absolutely right. So this portion goes to 0. Nice. Okay, now let's focus on the other piece. What happened to this portion right here? As t goes to infinity, what happens to that exponential term? Right, so it's also getting larger, right? So this is also going to infinity. But we're multiplying by a negative value, right, in the front. So what is the limit? Right, so Suman, you're right, it's negative infinity. So how does our solution behave? Well, we can say in conclusion, our solution approaches negative infinity as t approaches infinity. Okay, so that will be the statement we can make for this solution. Now again, if you have a graphic device, you can graph the solution and you'll see the behavior. It's going toward negative infinity as t approaches infinity. Okay, so again, you can always apply calculus to differential equations because everything kind of go together. Okay, so any questions on this? Alright, so that's the end of 3.1. Just solving homogeneous constant coefficient of second order. Okay? So now I'm gonna... Go ahead.
Are you recording the session?
Yeah, I think so.
Wait, but I don't see it.
Well, you won't see the recording. It's recording in a different device.
Oh, okay.
Yeah, but you see my screen only, right?
Yeah.
So I'm trying a different device today. It's from one of my friends. So let's see how it goes. Okay, and now I'll upload the video if I have the recording right. Hopefully it's recording after class, and then you can look it over if you want to. Okay, they'll be on my YouTube video. All right, so any questions on solving second order homogeneous constant coefficient differential equations? So, okay, so let's move on to 3.2. So before I move on to 3.2, I'm going to give you a brief summary of 3.1 so far. So in conclusion, if we're given a second order differential equation, say a y double prime plus by prime plus cy equals to 0, where a, b, and c are real numbers, right? So they're constants. We assume that the solution form is y equals e to the rt. If we assume that, then we know y prime is equal to r e to the rt, y double prime is r squared e to the rt. So then we have the following equations: e to the rt times a r squared plus br plus c equals to 0. And this is what we call the characteristic polynomial. And this characteristic has, so the characteristic polynomial has, so one, it could have real distinct roots. So that means R1 is not equal to R2. That's the case we saw today, where we have R1 is different real root from R2. Now it can also have real roots, but repeated real, right? Meaning R1, so the little r1. R1 is exactly equal to R2. So that's going to be for the future. We're going to study this in, I think it's 3.4, but I'm not sure, maybe 3.5. Or it could have no real roots, but complex roots, right? So we can have complex. So this means complex roots. And we're also going to study that in 3.3, I believe. So these are the two different cases that are left to go over, but those are for the future sections. Right now we only covered that if you have a characteristic polynomial, if the roots are real, distinct, we know how to write the solution to that homogeneous equation. So that's the conclusion for 3.1. Now, moving on to section 3.2. So 3.2 is more theoretical materials. We won't be doing much of computation because we want to talk about the theories behind second order differential equations. So 3.2, so the book titles it as the Wronskian. So that's another concept that I'm going to explain later. The Wronskian. So I'm gonna call it N theories, because we're gonna be talking about a lot of theoretical component to this subsection. So let's start off with 3.1, the theorem 3, the first one, not 3.1. It's a 3.2.1, the first theorem in 3.2. So this is theorem 3.2.1, the first theorem. So for this theorem, you don't have to know the proof, but you should understand the statement. It's very important because this is one of the theorems that guarantees us a solution to second order differential equations and existence of the solution. So just like we had it for first order, if you remember, on the first order we talked about a uniqueness and existence theorem. So do you guys recall that from chapter 2? Alright, so if you remember that, the same theorem we now extend it to second order. Okay, so here's the formal statement. So consider the initial value problem. So suppose you have a general initial value problem, y double prime plus p of t times y prime plus q of t times y is equal to g of t, with the initial conditions y evaluated at some t naught is equal to y naught and y prime evaluated at t naught is equal to y naught prime. Okay, so these are just notation where p, q, and g, so and g are continuous on an open interval I that contains the point t naught, then there is exactly one solution, which we're going to call it y equals to some phi of t, some function, right, of this problem. And the solution exists throughout the interval I. So very similar to what we had for first order, but now we're applying to a second order differential equation. So we want to make sure that P, Q, and G are continuous on some open interval I that contains the initial point t naught. Then we can say that there exists one solution, y equals phi of t, some function of t, and the solution exists throughout the interval. So here are the key points from the theorem. So the key ideas from this theorem. So one is that it has a unique solution, right? Why we're calling a unique solution? Because it has exactly one solution within that interval. So that solution is unique. So that's why we call it uniqueness and existence theorem. So I didn't write that here, but let me mention it. Existence and uniqueness. So this theorem is the existence and uniqueness theorem. So the first key idea is that it has a unique solution. So that's the first key point. The second key point from this theorem is that the solution exists, right? There exists. So okay, so that's the other key point. And then we can say that the solution that exists is phi, a function of t. So that's what we call this the existent and uniqueness theorem. So these are the two key ideas that we can take from this theorem. Now, how do we apply this theorem to a problem? Okay, so let's look at a problem. So let's do an example. Now, before I move on to an example, for this one, you don't need to know the proof. So okay, so we can ignore that part. But the next two, I'm going to prove them to you because we have to kind of know the proof. Okay, so let's see how this is useful for an example. So here's an example to illustrate this. So let's find the largest or the longest interval in which the solution of the initial value problem so t squared minus 3t y prime plus t y prime minus t plus 3y equals to 0, and y of 1 is 2 and y prime of 1 is 1. So find the longest interval in which the solution of the initial value problem is certain to exist. Okay, so here's a problem, and we want to determine the interval where we have a unique solution, and that solution is, it exists. Okay, so existent and uniqueness can be applied. So we want to write it in this form: y double prime plus p of t y prime plus q of t times y is equal to some function g of t. So I'm going to go ahead and rewrite the given equation. So if I were to rewrite it, we have y double prime plus t over, and I'm going to factor t squared minus 3t this way, so t minus t times t minus 3 y prime minus t plus 3 over t minus 3 times t times y is equal to 0, so still be 0. Okay, so I rewrote it in the form that we were looking for, which we can call a standard form, right? Where the derivative has the second derivative has the coefficient 1. So now, so p of t, g of t, and q of t are right here. So here's p, here is q, and g is 0, so that's nice. So what is this function discontinuous? So let me rewrite the equation one more time. So y double prime plus, I can cancel out the t's, So we have 1 over t minus 3y prime minus, so the second one doesn't simplify, and t times t minus 3 y equals to 0. So Gabriel and Suman, you guys are right. So both, so p of t is discontinuous at 3. Q of t is discontinuous at 0 and 3. So that means we have to remove 0 and 3 for both of these functions to be continuous. So discontinuity at t equals 0 and 3. So that means the interval that these functions are continuous, it's going to be negative infinity to 0, union 0 to 3, union 3 to infinity. So this is where both of these functions are continuous. Anik?
So professor, in the second line, I think the expression is t times t minus 3, or I don't know.
T times t minus 3. Yeah. Did I copy it wrong? No, right? Yeah. That's the function q of t. Yep. Right? So
I didn't get that.
So this function right here, it doesn't simplify. So the discontinuity is when t is 0 and when t is 3. Because t minus 3 will be 0 when t is equal to 3.
I got it.
Okay.
So, oh yeah, I got it. Thank you.
Alright. Alright, no problem. And then p, which we're calling this function, this is discontinuous when t is 3. So the discontinuity is at 0 and 3, right? So the interval where this function is continuous is the interval I just wrote down. Well, now let's look at what is t naught. Well, t naught is given in this problem is 1, right? And where does this fall into? Which interval? Right, so Gabriel, no, so that was the answer to the previous question. So Imrose, yes. So the interval this fall into, so that's the symbol. So I'm just going to give you one more symbol. So this little epsilon looking symbol, it means it belongs to the interval 0 to 3. So this is a mathematical symbol, it means belongs to. Okay, so 1 belongs to the interval 0 and 3. So Alex, you're also right. So the solution exists and it's unique is on the interval 0 to 3. We don't have to compute the solution, so we just want to write out that it is certain to exist and that is unique. So this is guaranteed by theorem 3.2.1. So any questions? So very similar to what we did for second order, but now you're just looking at more functions, not just one, whereas first order it's much more a bit simpler than second order, right? And you can just generalize it to nth order derivatives, so we'll do that in the future. Okay, so let's do one more example for applying this theorem. So here's another problem that we can do. So this is also from our textbook, one of the homework problem I recommended. So same direction. Okay, so same direction, right? I'm not gonna write them. Find the largest interval, so I'm just putting ... where the solution to the initial value problem is certain to exist and it's unique. So let's do, so why don't we go ahead and do, let's see. So here's a problem from our text. So we had this problem, y double prime plus cosine of t y prime plus 3 ln of t times y equals to 0, and initial condition y of 2 is equal to 3 and y prime of 2 is equal to 1. So so these dot 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 means that it's the same instruction from the previous problem. So we want to find the longest interval in which the solution to this initial value problem is certain to exist. Okay, so I'll give you guys a minute to think about this. Okay, so what do you guys think? Where are these functions continuous?
I think it's from 0 to infinity.
Mm-hmm. Right. So why is it 0 to infinity?
Look
Would it
at
be because
cosine.
of ln?
Okay. So I heard someone said ln. Sadia, were you saying something?
Okay, so if we look at the domain of cosine of t, we know that it's continuous from negative infinity. I mean, it's from negative infinity to infinity, but 3 times ln of t is undefined at 0. So
Mm-hmm.
based on that, if you look at the continuity of two functions, you could say that it's from negative infinity to 0, union 0 to infinity. But t, the value for t, which is equal to 2, that exists from 0 to infinity,
Right.
which is unique. Yeah.
Exactly. So both of you have it right. So the interval where both P and Q are continuous, it's going to be 0 to infinity because ln will restrict it more, right? Now our initial point T naught is 2. Well, that is in the interval 0 to infinity. So therefore we said that we have a unique solution and it exists guaranteed by theorem 3.2. So using theorem 3.2.1, it's going to be on the interval 0 to infinity. So that will be our, oh, that's funny. So that will be the answer to this problem. So any questions on this? Okay. All right. So that's 3.2.1. So web work doesn't do much on 3.2.1 on this. So if you want to look up your recommended textbook questions, you can also do that. Oh, by the way, guys, I saw a lot of you didn't do 2.9. I said you have to do them, at least some of it. I didn't say ignore it completely, right? So if you're one of those who didn't do it, please do it, because 2.9 you still need to know those materials, right? So send me an email and I'll open up the section again for just for those who didn't do it. I always do 50%, okay? Alright, so everything else is you guys catching up on, so that's good. Alright, so now moving on to the second theorem. Now for this one, you have to know the proof as well, okay? So let me state the formal statement and then I'll start writing the proof. So this one is theorem 3.2.2. This is a very important theorem again. This one has a name as well. So this one is called principle of superposition. So any theorem that has name next to them, they're kind of important. That's one way to tell if it's important or not. So just for your reference. So this one has a name, principle of superposition. So we know what superposition is, right? So when I give you the linear combination of y1 and y2 on section 3.1, so this is written down in a formal statement for us. So consider, so if y1 and y2 are two solutions to the differential equation, so L of y, so this is another notation I'm introducing, which is y double prime plus p of t times y prime plus q of t times y equals to 0. So that's what we're calling L of y. Then the linear combination of so the linear combination, which means if you take a constant multiple of y1 and y2 and add them up, so c1 y1 plus c2 y2 is also a solution, which we saw in 3.1, right? We just kind of wrote down the general solution, but we didn't really prove it. Is it really a solution, right? So this is when we're going to prove it. So also a solution for any values of the constants C1 and C2, okay? So regardless of the values for C1 and C2, we want to show that the linear combination of y1 and y2 is also a solution. So that's the statement I'm going to prove next class. So we'll continue this tomorrow. Okay. Now, I do want to give you a heads up on where we're going. So, have you guys heard of Kramer's rule? Yeah. Okay, so that's great. Now, those of you who haven't, you can also do a little research. So, research about Kramer's rule. So in algebra, we use Kramer's rule to solve a system of equations. It could be 2 variable, 3 variable, 4 variables would be complicated, but I think the most we went up to was 3 variable. And then you also saw a concept about determinant in calculus. Have you guys heard of that term? Okay, so Alex says yes. So research about Kramer's rule and determinant. Okay, so these are the two things that I want you to look up on your own before I introduce them, because Theorem 3.2.2 is going to show us a really nice proof to why the linear combination of y1 and y2 is also a solution, and that solution is, we're calling it a general solution. Now, why is it the general solution? Can there be another form of a different solution to this differential equation? So that's where the question is going to come in, and we're going to use the concept, or we're going to learn the concept of a Wronskian, which is really nothing other than the determinant of the system, which I'm gonna show you next time. So that's why I want you to have a little recap on what is the Kramer's rule for a system. Let's say 2 by 2 by 2 matrix. Okay, so you don't have to look up 3 by 3, but if you want to, you can extend that to 3 by 3. But I just want you to look up 2 by 2 matrix, have just a general idea how do you solve it, right? And look up determinant of also for a 2 by 2 matrix. So that way when I do the proof, hopefully the notation and the idea behind it, everything will kind of fall in together. Okay, so that's where we're headed next time, and then we'll do some computation using Wronskian, and I will do one last proof. That'll be 3.2.7, and then move on to complex root. So that's for next time. All right, so any questions, guys? So we have 2 more minutes before you start your quiz. So if you want to take a break, come back in, go ahead and do that now. If not, then let me know if you guys have any questions.